Hi everyone, this is lecture 5 and we are going to start talking about boosting, okay? So this is basically an introduction to boosting, and here we have some references. All these references you can download from our Google Drive folder, okay? So boosting is a greedy algorithm for additive models. So let's start defining what a greedy algorithm is. A greedy algorithm is an algorithm paradigm that follows the problem-solving heuristic of making the locally optimal choice at each stage with the hope of finding a global optimal. So, in other words, we try to reach to a global optimal solution by several steps reaching local solutions. So we kind of sequentially get to local solution in order to in the end of this path to reach a global solution. Okay, so we can interpret this as a stepwise method. So in many problems, this greedy algorithm, this greedy strategy will not produce an optimal solution, but it may yield a solution that's locally optimal, but is good enough to approximate the global optimal solution in a reasonable computing time. Okay. Right. So now we know what a greedy algorithm is. So let's look into additive models. So basically, an additive model, we can define it very broadly for nonlinear mapping between x and y. So we have y is our dependent variable, we have x as our vector of covariates, explanatory variables, and u is the error term. So if we express this function f as a linear combination of functions f of m, so we have like capital M functions f, and we are linearly combining these functions. This is an additive model, okay? And these functions f of m, we call them the basis functions or the weak learner. And the idea here is that we are going to approximate the function f by simpler functions. That's why we call them weak learners. So we are going to combine, we are going to have an ensemble of models that are not globally optimal, but when we combine them, we have an aim to reach a global optimal solution. Okay, so it's like divide and conquer. So we are going to start with simple and not very good models, so that's why we call them weak learners. But once we combine these models, we can have, in the end of the day, a very, very powerful solution. Okay, and the origin of this method is on classification problems, but here we are going to use it for regression problems. Okay, in this lecture we are going to focus on linear models, so boosting applied to linear specifications. Later in this course we are going to use boosting to specify nonlinear models like regression trees or neural networks and so on and so forth, right? But here, to keep things simple and for you to get an understanding of the ideas behind boosting, we are going to focus solely on linear specifications. Okay. So what's the goal when we talk about global optimality? What we want? What's our target? So basically, we want to estimate an optimal function f star, which is the minimizer of the expected loss function between y and f of x. Okay, so we define a loss function. So the method is quite general, And here we are going to see that we are going to work with very specific loss functions, okay? But it's a general method. So once you grasp the idea of boosting, you can apply it to a myriad of models and different loss functions, okay? So it's very versatile. It's a very versatile method, okay? So here we're going to consider the quadratic loss. So basically, we define that L of y and f of x is the square loss, okay? So it would be y minus f of x, the square of it, okay? So that will be our loss function, or we can write this as the square L2 norm in vector form. Okay? So our goal is to estimate the expected value of y conditional on x. We want to approximate the conditional expectation. Okay? So let me try to illustrate the boosting algorithm with an analogy to golf. So let's play golf. So imagine that you want to hit a ball into the hole, okay? But of course you don't want to do it in a single stroke. So our final goal is to send the ball into the hole, but we are going to do that in multiple steps. So imagine that you hit the ball and through in the direction of the goal, and let's measure our performance, how far we are from our target with a square loss, with a mean squared error cost, okay? And this is what's plotted by the blue curve. Let's assume that the ball is y hat, is your prediction, and y is the hole, is the target. So you want to get a prediction as close to the target as possible. So you hit the ball once, you get to that point here, still far from the goal, that's the hole, your target, okay? And you have an associated mean squared error that's here, that's for the MSE for the first stroke, and that's your initial function f hat at the first iteration, okay? Then you hit the ball again, so you have another function f1, that's the previous approximation that you had, that you were here, plus something, plus a delta. So this is delta 1, okay? So you get closer to the hole, okay? That's your second stroke. Then you continue and you hit the ball again. You were here and then you move to here. So the first ball you were here, the second ball you were here. You hit the ball again and then you reach this point here. So as I mentioned, this is delta 1, this is delta 2. Okay? That was the third stroke. And then you are getting closer to the hole, but now you pass the hole. So you're going to try a fourth stroke that it's going to get you here. Then you pass the hole again, and then you're going to hit the ball one more time, and then bingo, you reach the hole. Okay? That's exactly what we are going to do with boosting. We have a target, okay? That's our dependent variable y. We have a model, y hat, okay? In our first iteration, we are going to estimate a very weak model that may put us very far from the target. So the first error y hat minus y in the first iteration, that will be the first stroke, can be very far away, but closer than we were before. So we are not moving further away, but we are moving closer to our target. We are trying to get closer to it, okay? So we got closer, and then after that we are going to, okay, now we are going to measure the distance between the new point we are and the target. And then we are going to estimate a model again to get us even closer. And we continue like this until we are close enough by some metric. Of course, we can be very tough with ourselves and say that we are going to stop when we reach 0, when y hat is exactly equal to y, so reach the target perfectly, or we may have some kind of, difference that's small, and then we stop. We are close enough, we are happy. So that's the idea of boosting. But how we move towards our target? Remember that we need another ingredient. We need the target, but we need the cost, right? We need the function that's going to measure how far we are from the target. The distance between our model and the target. So in our case, it will be the MSE cost. So what we should look, we want clearly to minimize the MSE. We want to reach a point where MSE is 0 or close enough to 0. So how we move in the direction of minimizing this cost? That will be the negative of the gradient. So we are going to use the gradient. The gradient will be our guideline, okay? It will be the measure that will give us the north. Where should we go? Where should we hit the balls? We should send the ball in the direction of the hole, not far apart from the hole. And the gradient will give us this information. So that's why we are going to call the method gradient boosting. Okay? So that's the idea. Okay? I hope it's clear. So what we are going to do, so f hat will be the minimizer of the empirical risk, right? So we cannot have the true expected value. We are going to estimate it. So we are going to estimate the expected value of the loss function by the sample average of the loss function. This is the empirical risk. And for the quadratic loss, look who is the empirical risk. It's just the 1 over t, the sum, what we have here inside. What's this thing here? That's just ut. So RT is equal to 1 over t ut squared. Okay? So we are minimizing the squared error, the average squared error. So that's why we have the mean squared error loss. Okay? And R is called the empirical risk function. So the method is easy to adjust for different choice of loss functions. As I'm going to show you in linear models, boosting can also work as a variable selection procedure. It is useful when p is much larger than t. We can, for instance, define our function as an additive model with a single regressor. So, for instance, if we have p much larger than t, we can define individual functions for each regressor, so no interactions here. But of course, you can make it more complicated by making interactions, but that's an idea. We are going to look into that when we move to nonlinear models, okay? But here, as I mentioned, we are going to keep things simple, and we are going to apply this method to linear specifications. And it's really robust to multicollinearity, and I'm going to show you why. So this is an advantage, so you can have highly correlated errors, and the procedure is viable. You can implement it, you can run it, okay? And it will optimize the predictive power, okay? So it's good. So it's basically an iterative algorithm. So the idea is to use the gradient to minimize the empirical risk. So we start with an initial solution, so our initial guess, okay? This can be really easy. We can just say that the initial guess it will be y bar. That will be 1 over t sum of yt t equals to 1 to t, if you wish. Okay, so pretty simple. Just initialize the method with the mean. Okay, and at every iteration you're going to update your function. So this is your approximation for each time period or each unit that you have in your sample. You're going to say at the iteration j, okay, your estimated model is going to be the estimated model from previous iteration. So this is current iteration. This is previous iteration. Okay? Plus what? Remember, we have to move towards the hole. Let's play golf. We are moving towards the hole, not far apart. So how we move towards the hole? We have to use information from the gradient, more specifically, minus the gradient. Okay? So we are going to take the derivatives of the empirical risk with respect to each function, to the learner, to the weak learner, the f, take the negative value and evaluate it at the estimated model. So we are going to update, okay? So we update the previous iteration fit with the negative of the gradient, okay, evaluated the current point, times a step length. Why does the step length is important? Let's go back to our golf example. Okay? Imagine that when we were at this point here, we hit the ball too strong. So you can go much further away than the hole. But now imagine that so we have to go back. So the gradient points into this direction. So you hit the ball again. But then you give a very strong hit on the ball and then you go here. So you end up further away than we were in the beginning. So we have to keep a balance. So we don't need just to go in the direction of the gradient and just sit. So we need to balance, we need to dose. So there's a need of a dosage of how much we are going to move towards the hole in the golf example. So what's going to control for that is exactly the parameter nu, this fellow here. The problem that nu too large, we are going to go further away. Nu too small, it will take forever to get to the hole. Eventually, we are going to get it, but maybe it will, depending on how difficult is the problem, it may take ages. So again, there is a balance. This is a tuning parameter that we are going to choose in practice. Okay, there are some rule of thumbs on how to choose it. It's better to keep it small than large, because if it's small, the only harm that you're going to take forever, but you're not going to miss the hole. If you put it too large, you're going to go back and forth, back and forth, back and forth, and never reach the hole. Okay, so, but we are going to talk about this a little bit later. Okay, so how is the algorithm of the gradient boosting? So we first, remember, we have a function. It's not writing, what's going on? Oops, bug on my pen, sorry about that, so no pen. So we want to estimate the function y. Okay, pen is back. Okay, so what's y is y1 to yt. Okay, so we want to get to this target. This is our target. Okay, so we need an initial guess about that to initialize the algorithm. So let's say that we say that, okay, the first one, that will be f1 hat at iteration 0 and ft hat at iteration 0. We have to initialize this. So we can set it to 0, to a constant. You can choose, the algorithm will adapt on that. So like one of the good initializations, remember the first lecture when we have nothing to say, just guess the mean. Okay, so we can like put the same thing all together and say this is y hat, y hat, y hat. So we basically, we set a constant term. So we start from the mean. Okay, and we have an initial value. So what we have to do now, let's take the derivative of the loss function multiplied by -1. But in our case here, remember, if L is quadratic, okay, minus DDF of L is just what? 2 times the error. Okay? That's our loss function. The 2 is innocuous, you can just skip it. Okay? So what's going to be the derivative, the gradient, will be the vector of errors. So in our case here, what's going to be, is going to be at iteration 0, okay? It's going to be y minus y hat. So basically we are demeaning the data. That's the first step, okay? And then we have these vectors of u's, okay, that were evaluated at y equal yt and f equals with the first fit. Okay? So what's that? What we are saying here, okay? We made the initial guess, and now we are measuring with this initial guess how far we are from our target, how far we are from the hole in the golf analogy. And we are going to take this. The third step is the following. Okay, so now what we are going to do? We are going to take a weak learner, a model. Okay, could be linear, could be nonlinear, any weak learner. It should be easy to estimate. And we are going to fit the error. What's the error? Is the remaining distance from our ball and the hole. So remember, here is the hole, flag, the hole. We are initially here, we hit the ball, we had it here, okay? So this is our first iteration, and that's the error. So now we want to construct a model to fit the error, okay? So we are going to take the weak learner that best fits the residual, the error, the remaining distance, okay? But maybe in one step it won't be enough to get to the target, to get to the hole, okay? So we update the function. So at new iteration, it will be the one from the previous iteration plus the fitted value of the arrow. So it's the second hit. How much we could get with the second hit to get to the target. Okay? So this is exactly a constant times the second hit, the second stroke. Okay? And this new will be a constant between 0 and 1. Okay? We do that, we update the fit, we repeat steps 2 to 4 until maximum iterations is reached, or if we get a very small error, so we get close enough to the target, and many ways to stop the algorithm. Okay? And remember, what's step 2 is to compute the gradient, which be the error. So at the third iteration will be the error, the distance to the hole after 2 strokes. Okay? And we want to fit that remaining difference. And we are going to continue like this. Okay? So that's the algorithm. So now let's imagine that we have a linear model. So our weak learner is a linear model. Okay? And suppose that at each iteration we have like p covariates. Okay? P can be large, very large. Okay? So what we are going to do? We start with the average. So j equal to 0, f hat 0 is y hat. Okay? So now what we have? We have u hat 0, that's going to be y minus y hat. So we are going to take this residual and we are going to fit an univariate regression. We are going to regress the residual at iteration 0 on x1, on x2, on x3, on xk, and up to xp. We are going to run p univariate regressions. We are going to select the one that minimizes the cost function. Okay? So let's say that the one that minimizes the cost function is xk. So what we are going to do? So we are fitting this one here. So what's going to be the error on the first iteration? Would be y hat minus u bar minus what? xk, xk beta k hat. That's the OLS fit of y minus y bar on xk. We take this residual again and we continue like this. It's called component-wise algorithm because it's fit for linear models, okay, where the weak learner is a simple univariate regression. And at each step, we are going to pick the regressor that fits the error term the best. Okay? So we are trying to, you can imagine, now you can see like the full definition. We have a global model that could be a linear model with many regressors. We don't know which regressor should we include, so we start one by one. So before we have no regressors, we choose the one that fits the data the best, we select this one, we compute the error, and then we are going to select again what's the regressor that fits this error the best, and we continue like this, so on and so forth until convergence. One important point: once we select a regressor, like here we select regressor xk, we do not remove xk from the list. Xk continues in the list, so we can select xk again, okay, in the second step, and on the third step, on the fourth step. So why can we do that? This will be a question for you to answer during our live session. So we are going to have some questions for you to think about that you are going to discuss with your colleagues during the live session, and you're going to come up to a conclusion. Okay? So this is going to be the first one. I'm going to send emails about that. Okay? So let's look at an example. So here we have a nonlinear model, which is written on the top of the plot. We start with iteration 0, so it's just a constant fit, it's the average. That's the red line that you see on the plot. Okay, the true model is the one that you see with dashed green curve. The dots are the data. Okay, and the model is here. Okay, and on your right, you see the residuals from this constant model. So basically here in this setup, it's doing nothing, okay? Because the mean is 0, so you're removing 0 from the data, so it's doing nothing. First step, we fit a model. What's the weak learner here? Of course, it's not a linear model, it's a polynomial, okay? Because this is a nonlinear function. So you see that the first fit is pretty bad. See, it's the red curve on the left plot. So we took the residuals from that. That's on your right, and then fit a second model, a second weak learner. That's the red line again, and we continue like this: iteration 2, iteration 3, iteration 10, iteration 20. We're still far from approximating the green dashed line, but we are getting closer. 30, 150, pretty close, huh? So basically what we have as residual is something that's constant. So basically no further improvement. So that's the idea. It's like to making your model more complicated at each step, but each step should be very simple, which should be a local approximation, but in the end we can have a very complex model that will deliver, hopefully, a global solution. Okay? That's the idea of boosting. So it's clear from the step 4 that at the last iteration, iteration capital J, our fitted model will be the first guess plus a sum, basically a weighted sum with this constant nu of the fitted residuals, right? So the structure of the prediction function will depend on the choice of the weak learners, okay? Because these u hats will be the fit of the weak learner. If we have linear learners, we're going to have a linear function. If we have smooth learners, we are going to have a smooth function, okay? It does variable selection, and it's useful when p is much larger than t. And one thing that's important is that if j goes to infinity, the algorithm will select all variables. So we have to put a control on that. And that's the second question for our live session. Why? As j goes to infinity, the algorithm will select irrelevant regressors. Okay? That's for you to think about. Solution for that, we have to consider some early stopping or cross-validation or some information criteria that for linear models, we can derive information criteria for boosting, okay? And let me give you an example with linear learners. Let's suppose that we have 3 regressors, x1, x2, and x3, and so 3 linear learners. Let's assume that we have like 5 iterations. So imagine that we have a hypothetical solution where x1 is selected at iterations 1, 2, and 5, and x3 is selected at iterations 3 and 4. So basically, what we have here is that the final fitted model will be the initial one here, plus all the fitted weak learners, okay? But what's you had 0 is just a linear model on x1, because x1 is selected iterations 1, 2, and 5. Okay? And then we have it again at iteration 2, and then we have at iteration 5. But then at iterations 3 and 4, we have x3. So in the end, our model is going to be linear, but it's going to be a beta 1 on x1, a beta 3 on x3. But what's beta 1 is nu times the OLS coefficient, the OLS estimator from model at iteration 1, at iteration 2, and iteration 5, and beta 3 will be nu times the OLS estimator of iteration 3 and iteration 4. Okay? Another question that's related to the first question. Why? We know that when we estimate something by OLS, we make the residuals orthogonal to that regressor. Okay? So if we run a regression of x on beta plus u, we know by construction that OLS implies, okay, that x times u hat is identically equal to 0. Okay? So basically say that if we regress y on x1, the residual will be orthogonal to x1. So how on earth it's possible to select x1 again here and here if we have already chosen x1 in the first iteration? Do you have an answer for that? I guarantee that the answer is on this slide. Okay, if you look careful at the fit, but I'm going to keep you curious, or you have to think about, and we are going to discuss this on Friday. Okay. Stopping criteria. Let's consider the component-wise boosting linear models, and at each iteration we select a single regressor. Okay. So if we define a matrix H, that's for each covariate that we have, that will be xy times xy prime, everything to the power of 2, divided by the L2 normal xy, and we define bj as this expression that looks ugly. Okay, we can show, basically, we can define a modified information criteria for the j variable, at iteration j, that's going to be the log of the residuals of this iteration plus a ratio that will involve the trace of this beta. So basically what we are measuring the marginal contribution of each new step, and this is kind of the degrees of freedom of the boosting. Okay, this can be estimated for this component-wise linear boosting in this specific setup. So we can monitor at each new iteration if the AIC is going up or down. If it's still going down, we keep the iteration. When it reverts and it goes up, we stop. Okay, that's an idea. Or if you don't think this is monotone, you can run up to m iterations, but then you look at when the iterations get to the minimum AIC, and then you stop. There is your stopping point for the algorithm. Okay, there's these possibilities. Or you can do cross-validation if you are in an IID framework. But the same criticism that I mentioned about cross-validation with Lasso and Ridge and all these methods will apply here. Okay? Some theory. Unfortunately, there's no much theory for dependent data, and I'm going to go very briefly here. Okay, we can derive some bounds if we have IID data with fixed regressors. Okay, and basically what can be shown if we have some assumptions on how the variables grow, and if we fix the covariates and we make the covariates unit like the 1 over t sum of xtj square equals to 1, so we put like everything normalized, and if the model is sparse, so it's the same kind of sparsity condition that we have for the lasso, and if we have some bounds here on the Hessian, so something like the restricted eigenvalue condition, okay, and basically we show that 4 and 5, like the errors are normal. We kind of controlling the signal to noise ratio. Okay, we can get this ugly theorem, but one thing that's important, as j goes to infinity, j grows. Okay, and if it grows at a specific rate, we have prediction consistency. Basically, boosting works. Okay, and depending on ugly constants, the convergence rate can be the same as the slow rate of the lasso. So this is the slow rate of the lasso. Okay? And so be the maximum of the two. So it's close related to lasso under very specific setups. Okay, we can also compare directly. So the rate is best for delta larger than 0. What's delta? Is a constant that will appear in how we grow the algorithm. Okay, and what matters in terms of practice is that lasso for linear models is equivalent to boosting. They have a kind of close connection. Okay, so one question that you may think, why should I use boosting instead of lasso, or vice versa? My point is that with lasso now, there's no need to use boosting with linear models. Okay, boosting will be extremely useful, but really extremely useful for nonlinear models. Okay? So not for linear models. For linear models, you may keep lasso and friends. And then you may ask the question, but why on earth, Marcelo, you are teaching this boosting now? Because boosting is an ensemble method, and boosting is better understood in the linear framework. So if you understand how the algorithm works in the linear framework, when I explain to you guys how to use boosting with regression trees or neural network models, it's going to be much easier. Okay, so consider that as a step in between. That's why in the next assignment, I haven't asked you to run any boosting. I just asked you to run bagging and complete subset regression. And the reason is because there's no point in doing boosting if you have lasso. Okay, it's going to be more or less the same. Okay, so that's basically the theoretical results. Okay, let me go very fast through an empirical example. I know you like applications. This was a paper published in 2009 in the Journal of Applied Econometrics, and the idea is to select factors to predict macroeconomic variables. Okay, So the idea is that you have a large set of variables, of economic variables, and one approach that we are going to see in details further in the course is to construct principal components for these variables, okay? So basically eigenvalue decomposition. So these principal components that are going to call them gamma are kind of summarizing the information. So the authors consider if you have a variable y that you want to forecast, you may use lagged y's plus some factors. Okay? These factors can be principal components of the x's, can be the x's themselves, can be squared values of the x's, or squared values of the principal components. There are possibilities. So what they do is that instead of like taking the two most important principal components, why not looking at all of the principal components and let the algorithm, the boosting algorithm, like the component-wise boosting, pick one of them, okay? And we can select lags. So they tried two things. One that may select completely different lags at each step, and a second one that's a block that you select all the lags of a specific regressor. Okay, so one is what they call component-wise boosting, and the other one is the block-wise boosting. Okay, and I'm going to show results for inflation, federal funds rates, industrial production, and employment. They are looking for 12 steps ahead, so 1 year ahead. Data from 1960 to 2003. What's the axis? 132 macroeconomic predictors. Okay, and they have the following choices for these factors F that I showed you in the previous slide. Can be the raw data, the axis plus squared values of the axis, all the principal components of the axis, the principal components and the squared principal components, and can be the principal components of the axis, the squares and the lags, and the principal components of the x, squares, and the lags, and the squared principal components. Okay, so like all the possibilities. Okay, and the benchmark is a pure AR4 model. Okay. And also standard principal component. Just use the principal component with nothing else. That's called the diffusion index. That's DI there on the slides, means diffusion index. That's the nickname for running a principal component regression in macroeconomics. Okay, so that's the results. And for inflation, okay, and basically what we want to look, it's want to minimize the adjusted BIC. So here what they found, the best model, they try all these combinations. It was like the boosting, okay, for the first step, the boosting for using all the axes, okay? The second one, all the axes. And then model 12 is the boosting with the extended principal components, where they put like lags and squares. The thing is, if we look here, the summary results, all methods beat the diffusion index, the pure principal components, okay? And so this is like the relative MSEs with respect to the AR4. So numbers less than 1 means that we overperform the AR4. Numbers over 1 we do not perform. So model 12 overperformed the benchmark in all cases. Model 3 outperformed the beginning, but not here, but it's not the best here anyway. Okay, so this is basically the big picture is boosting is doing better than just picking the three most important principal components, or just using an AR4. Okay, and this holds for all federal funds the same thing. Federal funds, the diffusion index is better just for in the first case. Okay, but for all the other samples, basically here is like the start and the end of the sample. Okay, and what we can see that in all the other cases, boosting doing better, and same thing for industrial production, same thing for employment. Okay, the paper is on our Google Drive folder. If you have interest, you may take a look on it. So that's for now for this first block. See you on block number 2.